my name's Arslan Atta.
My name is Jonathan Yu.
And my name is Todd Parker.
We are Embedded Team 5 for Spring 2018, and we created an automatically fetch and delivery system.
We were inspired to do this project by the Amazon automated delivery robots known as Kiva. They use these robots to pick up packages in their warehouses to deliver them from where they are stored to where they are being packaged for delivery. These robots work on a system where they know exactly where their target objects are and where they need to be delivered to. Our goal with our project was to take this system and this concept and bring it down to a smaller scale and see if we could find randomly located objects and items to deliver to where they need to be.
In order to implement our system, we designed a playing field that is divided into 3 separate zones. We have the playing field zone, which is the top 3 foot by 2 foot area of the zone. This will contain 5 blocks of different colors, red, green, and blue. We have a sorting zone, which is 3 foot by 6 inches, which the first rover will deliver the blocks in the playing zone to. Finally, we have 3 delivery zones, which are 1 foot by 6 inches each, where the second rover will deliver the blocks to based on their respective colors. There are several different observable behaviors and elements incorporated into our system. Rover 1's operation traverses the playing field and picks up objects one at a time as it moves them to the sorting zone. The rover will not cut diagonally across the playing field, but only move along the X and Y axes. Upon delivering an object into the zone, it resumes its operations and searches the playing field for other objects. Once an object has been placed into the sorting zone, Rover 2 begins operation. It picks up the objects in the sorting zone and delivers it to the correctly colored delivery area in the bottom section of the play area. Every time it moves an object into the correct zone, it returns to the home base on the far left side of the sorting zone and waits for another object to be placed. The diagram on this page is an example of a delivery run of this system. As you can see, Rover 1, which is indicated by the black block in the playing field, moves towards the green cube, which is then delivered into the sorting zone, following the path indicated by the arrows. After it has been placed into this area, it goes back to look for the red block, while Rover 2, indicated by the black block in the sorting zone, moves over to the green cube and sorts it into the proper zone. In this section, we will be giving a brief system overview. The following slides will break down the major aspects of this system as represented by a task diagram seen to the right. We will be reviewing major threads and interrupt handlers and why we chose the specific design that we did in order to make our system and project succeed.
The sensor mapping thread controls a servo-mounted IR sensor and maps out the location of objects detected on the playing field. The grabber thread controls a servo-mounted arm that can swivel to detach objects that are picked up by the Rover 1 and Rover 2. The Rover 1 motor control thread implements an algorithm to navigate through the play area, branching to located objects and delivering them to the sorting area. Similarly, the Rover 2 motor control thread implements an algorithm to navigate the sorting area as it detects objects placed there for delivery. The encoder thread uses a combination of encoded data from the rover and directions from the motor control threads to implement the algorithms in the other threads.
The pickup thread is similar to the grabber thread, except for the fact that it uses information from the pixie cam to determine whether or not to drop the object based on color. These last 2 threads simply act as information grabbers for the pickup thread.
Here we have some of our more important interrupt handlers. The sensor ISR reads the IR sensor values on Rover 1 and sends them to the IR mapping thread, which keeps track of the location of all the objects on the playing field. The encoder ISR pulls timers connected to the encoder square wave approximately every 100 milliseconds. This data will be passed to the encoder thread as the most recently measured motor rotations per second, as well as transmitting a short-term average value to the encoder thread. Finally, the PixieCam UR ISR will activate whenever the UART buffer receives data from the PixieCam and sends that data onto the PixieCam thread. Next, we will talk about how our hardware choices were made. Our first major hardware decision was on mapping sensors. We have two different setups for each rover since each one performs a different task in our system. On the first rover, we have a server-actuated IR sensor based on an algorithm developed at Sungkyung Kwan University in South Korea. Based on this algorithm, our IR sensor is rotated along a 90-degree arc by a servo, taking periodic sensor readings as it does so. By using our known rover location and the distance found to an object, we can then use the angle at which the servo is to calculate its approximate position in the actual playing field in an XY coordinate. This approach provides several advantages versus a fixed position sensor, some of which are listed here. Primarily, it allows us to cover a greater area with the sensors in a shorter amount of time to keep us from having to do multiple trips across the playing field, and it has a sweeping focus for a larger net to be cast for object location. Conversely, on the Rover 2, we have a single fixed position IR sensor. We use this because it has a simpler use case, having only to detect things in the sorting area, and so a simpler use case leads to a simpler design. This has several advantages in and of itself, such as complexity versus reliability, where the more complex something is, the less reliable it is, and the more likely something will go wrong. And a narrower focus allows for a more accurate reading along the length of the sorting area. Our second major area of hardware design choices came with the block pickup and release functionality. It consists of a hardware Hall effect sensor and a servo-mounted arm with a PixieCam and magnets. For those not familiar, a Hall effect sensor detects a changing magnetic field and therefore can detect whether or not a magnet is nearby. All of our blocks on the playing field will have a magnet on top, and we have a servo-mounted arm with a ferromagnetic material that will be attracted by the magnet and pick up the block. The PixieCam will determine the color of the block for where it needs to be placed, and the servo can move the mounted arm out of the way to disconnect from the top of the magnet on the block. The advantages of this design over something such as an electromagnet on the rover is that it's low power. It offers redundancy in the fact that we have the Hall effect sensor to always check to make sure that it's still there, and it is very simple, and as stated earlier, a simpler design is less likely to be faulty. Sense the location of the red block. And now that it's snapped on, it should take it all the way to the end. And we will see the first instance of the input lag as the servo waits for the Y position of the rover to be updated in the database. We can see that it'll wait an unfortunate bit of time. We found that the server, which we thought was using MongoDB, is actually storing everything in arrays.
A rotating IR sensor that read inputs from 18 different angles and took the sine or cosine at each angle to find the distance the object was away from the rover. Combined with the data I pulled from the server about the rover's current location, I could push the current locations of the objects in the field back to the server. The values would be averaged for each object I found, and there were 2 or more points per object. I also implemented a rotating magnetic arm that created a 10 centimeter buffer for where the object could be. This was beneficial because the IR sensor was only accurate to as close as 15 centimeters. We also attached the Hall effect sensor 5 centimeters below the attachment zone, so the sensor would pick up the magnets posted on the sidewalls of the object. The Hall effect sensor was very consistent, and the arm would not stop rotating until the Hall effect sensor picked up the object. This helped to move the objects until it was seen by the sensor. The servos did not appear to change in their angles as the battery drained, so the measured angles were used throughout. However, stepper motors would have been a better choice for how we use the servos.
The portion of the project that I was tasked with was the PixieCam. While this portion was not ready for integration, the PixieCam was able to communicate the color of the object in front of the PixieCam, so long as the object was within 15 centimeters of the PixieCam. One inconsistency that we experienced with the PixieCam was that, depending on the color of the light that the PixieCam was exposed to, the PixieCam may need recalibration to adjust to said lighting. However, if the light stays consistent among different runs of the project, the PixieCam will function as expected. For the sake of this project, however, an RGB sensor could have been used, since the only purpose of the PixieCam was to scan the color of the object in front of it. Another task that I later picked up was the navigation for the second rover. Given the correct conditions, for example, an object being dropped into the sorting zone, the pick would know where the next location to travel to was. However, while it did know approximately the correct location, it was not accurate enough for integration purposes.
To program the navigation control and motor thread of the first rover. This consisted of three major design areas: route mapping, motor control, and recalibration of the rover's internal position tracking. Firstly, for route mapping, the rover divides the playing field into a 9x6 array of 10 cm by 10 cm squares. Every time the navigation thread receives updated position values from the motor control thread, it increments a counter associated with its current grid location. Based on these counters, the rover moves in a serpentine path from the top left to the top right and back all the way down to the sorting zone. Upon encountering a target object, the rover branches from its current route to retrieve the object and take it to the sorting zone before resuming its search. To accomplish these sequence of movements, the rover implements a proportional integral control loop to set the speed of the motors and monitor their movement as a rough estimate of its position and angle. This leads into the final part of my contribution, which is the rover's recalibration based on sensor input of its XY location and its angle. When the rover senses an object within 5 centimeters of certain known locations, it identifies this object as a relocation beacon. Due to the ability of our IR sensor to rotate, we are able to then correct mistakes in the internal position state using high school level trigonometry where we sense the beacon and where we know the beacon is. Overall, these routines worked fairly well in concert. However, there were issues with them if the nav thread was not receiving fresh data from the server, or if the total error built up enough to cause the IR readings to be outside the 5 centimeter buffer. Given the chance to redo this design, I wouldn't change too much, other than adding another layer of redundancy to the rover position tracking, other than the motor encoders, and making server communication more robust and snappy. This concludes our presentation for Team 5. If you have any questions, please leave them in the comments below, and we will be sure to try and get back to you.